the first session under the theme of space technologies for water quality monitoring, which is on space technology and data for water quality monitoring and sustainable agriculture. We heard a little bit of the water-related extremes that we're experiencing increasingly all over the world. And in such a time, it is of utmost importance that we remain, that we keep the fresh water resources that we have clean. And with that said, I think a session on water quality is very critical. I would like to introduce the first speaker of the session, who is Stephen Greb, a researcher for the Space Science and Engineering Department of the University of Wisconsin-Madison, who's recently stepped down as the director of the Group on Earth Observations water quality initiative called GeoAqua Watch. Stephen Greb, the floor is yours. Thank you for coming.
Well, thank you, Nina. I want to thank Nina, and what a pleasure it is to be here today and participating in this conference. I've already met a lot of fascinating folks and people that are doing some amazing work in this field. So as Nina pointed out, this afternoon we're going to change gears and talk a little bit about water quality. Let me see how I can drive this thing here. Oh, it's already switched gears. So as she has mentioned, I'm Stephen Greb. I work at the University of Wisconsin in Madison, Wisconsin. I've also been director of GeoAqua Watch, and though recently have stepped down. So Wisconsin is almost exactly due north of here, 3,600 kilometers. And besides sharing a passion for water and water quality and trying to protect our water resources, we share with Costa Rica a number of birds. And not to get sidetracked here too much, but these birds, neotropical migrants, are birds that for the most part live here in Costa Rica. And once a year, they fly 3,600 kilometers to my backyard and nest and have their babies, and then they fly back to Costa Rica. So thank you for taking care of them the other 9 months of the year. And we enjoy having them. This Baltimore Oriole, this orange bird here, just showed up Saturday just before I was leaving to come here, ironically. So just to put this talk a little bit in context, some of these facts we've heard over the last day or so. About 1/3 of the world's water resources are in Latin America. Latin America is rich in water resources. And in some countries, the surface water accounts for a majority of the water supply that the country is using. Unfortunately, less than 40% of the wastewater is treated, and about 150 million people, or about a quarter of the Latin American Caribbean population, live in water scarce areas, and most notably the Central American Dry Corridor. And a number of areas do lack safe sanitation. And exacerbating this, of course, is a number of factors such as climate change, which is disrupting the water cycle, which we've heard about the last few days. Glaciers retreating, watersheds are degrading, of course, due to a number of reasons: pollution from effluent from factories and agricultural use, mining, what have you. And on top of all this, there's a dearth or a lack of water quality information. And I think as someone mentioned yesterday, it's hard for us to make sound decisions or how to manage our water resources without having the necessary information first. A number of you have asked me about Wisconsin, where it is and what happens there. And so I just put in a slide or two of Wisconsin. So we are in the north central part of the United States. We are blessed with a lot of great fresh water. we are bordered on the east side by Lake Michigan, one of the Great Lakes, on the north side by Lake Superior, our deepest Great Lake, and on the west by the Mississippi River. In addition to that, we have over 15,000 inland lakes, and of course, a number of rivers and streams to go with that. Our Department of Natural Resources came to us one year and said, you know, with staffing cuts and our shortages and resources, we're having a hard time keeping track of these lakes or what their water quality conditions are. Can satellite remote sensing help us? So we had launched this project, and now it's gone on for a number of years, but we started using Landsat, and it has since evolved. But we use satellites to monitor our 15,000 lakes because we just don't have staff to go out there and collect samples. So we also employ citizen science, and I haven't heard a lot of talk of that at this meeting yet, but we couldn't do this work without the citizen science folks, the people in the community that live on these lakes that actually are very good, very vigilant about getting out there and collecting samples for us. And we need that kind of information for validation and calibration and validation. And so we create maps like this. This is a map of Secudisc, or water clarity, for the northern part of our state. And you can see this is mosaic of different colors, which vary based on the water clarity of the lake. So I'm just going to do a 1-minute primer. And if you want to hear more about this, you'll come to Saturday's training session. But how we actually measure freshwater quality from satellites. Of course, the sun is our energy source. The energy from the sun coming in from, I guess it's from your right side there, goes into the water. It interacts with material in the water column. And a small portion of this energy comes off the surface. We call this emergent flux. And of course, goes up vertically to where it is intercepted by our satellite remote sensing sensor. There's a lot that goes on here. It's of course it's a pretty complex issue. Things like the scattering of the light, the moisture in the air, particulates in the air, a number of things kind of mask the symbol. But basically, we're measuring things in the water column that we call optically active, things like phytoplankton, chlorophyll, algae, suspended solids, turbidity, those kinds of things, plus the color of the water, which can be a measure of the organic matter in the water column. If we look at the water column, from the surface, we look down at the water, and we use what we call a spectroradiometer. And we look at the signal, the reflectance off the surface of the water. We see this squiggly line over the course of the visible wavelengths here. So, and we see peaks and valleys, and the squiggly line, or it could be called a fingerprint of that water, is unique to that water at that point in time. And these peaks and valleys are indicative of certain water quality parameters. You can see the peaks in this slide are indicative of total suspended matter, and the troughs or dips are indicative of chlorophyll, or the algae in the water, or phycocyanin related to the blue-green algae. We've gotten better at measuring water quality over time. The sensors have improved, and as you can see in this slide, going from the left to right, Landsat 7, 8, Sentinel-2, Sentinel-3, where once we had the potential, or could be called suitable, for measuring these water quality parameters, now we're out here at highly suitable. So we've gotten much better. A couple just key points about satellite remote sensing for water quality. It's great because it's a snapshot in time. It's looking at, in our case, where we have a high density of lakes, what is the water quality of all these lakes at this moment? And we can do comparative studies to look at the water quality, spatial and temporal changes in water quality for a number of water bodies. It's affordable. All what I'm talking about here are freely accessible, open access imagery. Once we develop an algorithm, and we use this over a number of years with some of these legacy satellites, such as Landsat, we can start to look at changes and trends in water quality. We can more and more, because of the rapid improvement in how we process this data, we're getting near real-time data, and our accuracy continues to improve. On the downside is these are inland waters tend to be optically really complex water, and it's hard to tease out the signal of the different materials in the water. We can see a potential interference from the bottom. We don't want to see the bottom. We want to just see the water column. Clouds. We hate clouds. Clouds are our nemesis. We can't do anything if it's cloudy. Get a drone, I guess. We can't see sometimes dynamic changes in water quality. We heard about some extreme flooding events. If that happens during a cloudy period, where it's cloudy for a week, we're not going to get any imagery to support that effort. As I mentioned, limited number of water quality parameters, things that are generally optically active, but things like temperature we're also very good at. Calibration and validation, we still need on the ground, boots on the ground to help us do it. Just as I said that, we needed to optimize the algorithms for the different ranges of water, optical water types, we call them, or different regions. We needed for validating these algorithms over the lifetime of the satellite, and also just to fill in some gaps that the satellite coverage we don't have. I would say there's 4 reasons why we see this rapid advancement of satellite remote sensing for water quality. And how's my time? 8 minutes. Okay, thank you. The 4 factors which I would contribute to this rapid advancement: 1, new sensor technology. 2nd, big data, cloud processing, our ability, the memory, the power of some of our computers and cloud processing. Algorithm advancement, we're seeing a lot more, of course, with machine learning and AI tools to process our data, and education and capacity development, things like this workshop here. I'd be remiss not to mention some of the great work and some of the great scientists here in Central and South America that are doing work on water quality using satellite remote sensing. I just cited a few of the papers here. There's many more, and there's some excellent scientists doing work in this area. Entrance ramp to data products. So one of the problems a lot of people have, that they want to get at this information, but they don't even know where to start. And it is hard. It's every time I pick this up and start looking at where things are at, things change. This is a quickly evolving area. So I've broken it down into 3 general categories. One are web apps, portals, places you can go and click and point, and it'll tell you what water quality or satellite remote sensing information is available for there. And I'm going to be talking about this, of course, more on Saturday. Probably these first 2 we'll be talking on Saturday. Second of all, PC softwares. There's a couple softwares out there which are freely available. CDAS and the one that the ESA Snap tool, which is ESA supported, where you can process these imagery yourself. And third is cloud resources, which I won't talk about, but was mentioned in some of the lightning talks, things like Google Earth Engine, some of the programs that are out there, some of the Python scripts, which now can be used to get at this information. I just threw in a couple regional images that I just pulled up last week or processed, just to show you, one, maybe the range, the spatial range of which we work. some of the imagery is quite wide and can help us look at water quality changes on a regional basis, such as this top one, which includes central and the northern part of South America. And then we can zoom down. The second panel on the bottom here is a Sentinel-2 image of Lake Nicaragua. Many of you have probably recognized it. This is a true color image. This is what it looks like. And then we've processed it for chlorophyll, TSS, and CDOM. And you can see this is the lake here, the two volcanoes that are out in the middle of the lake. See, it's spewing a little vapor coming out there. But it again, just showing some of the power of these tools. So I'm going to wrap it up there, but just put a plug in for Geo AquaWatch. I actually have some printouts here, just a one-page flyer on Geo AquaWatch. As it says here, our goal is to develop and build the global capacity and utility of Earth observations, water quality products, information to support the water resources management and decision makers around the world. So there's a number of folks that it's for the most part a best effort, volunteer effort, and there's folks right now that probably 300 to 400 people are part of Geo AquaWatch. So I would urge you to engage and become part of Geo AquaWatch. Here's the link to their website, and I'll quit there, Nina. Thank you.
Thank you very much for an inspiring presentation. And if you would like to learn more about this, a quick announcement. We still have 2 available spots for the training that takes place on space technologies for water quality monitoring, Earth observation data for water quality monitoring, hosted by Steve. Please approach us in case you're interested in joining. And is there any question from the audience, either on site or online, that you'd like to ask now? We will have a discussion later on, but please feel free to ask a question related to the presentation now. Shanlong Lu, please.
My question is that for some local application, the method will be very easy to use because we can easily find some verification data. And then if we're using your systems to globally or large regionally, how to find this kind of verification data? Do you have some ideas or ways? Yeah.
So validation of some of these global products has been an issue, is still an issue. We wrote a proposal and was funded by NASA to run a validation workshop in Madison. I guess it's been almost 2 years ago now. But the big issue is, where do we find this data? Who pays for that data? There are a couple databases out there. Of course, CBAS is the NASA database, which if you get a NASA-funded project, you have to put your data in CBAS. So that's there, but a lot of that, of course, is open ocean or even coastal water. Nima Pavelon from NASA Goddard has put together what he's called the Gloria database. Again, that's more inland and coastal waters. And then the University of Stirling in Scotland has a database, Limnades, it's called, which is strictly inland waters, I believe, and has varying degrees of access depending on, you might have to apply to get access to it, depending on what the source is. You have to be granted permission to use it. But you're right, this is an ongoing and an issue. One of the things we've talked about, and we haven't written the report yet, one of the recommendations will be kind of development of this global validation network, where people can, again, maybe through Geo AquaWatch, can come together and pool their their resources for these more regional and global projects. Hope that answers your question. Anything else?
Are there any questions from the online participants? No? Okay. We'll have a chance for more discussion after the three presentations. And without further ado, I would like to introduce the next speaker, Mahesh Champany from the International Water Management Institute in Sri Lanka. Mahesh is a researcher at the Institute. He's an expert in water quality and hydrological modeling and holds a joint PhD from UNU Flores. That's the United Nations University Flux Analysis Considering Global Group, Considering Global Change Assessment Unit at the University of Dresden. And Mahesh will present remote sensing estimations of water quality dynamics in the Asian megadeltas. I'm curious to hear more about that. Mahesh, the floor is yours.
Thank you, Nina, for the brief introduction. So just before I start, actually, I have to say, GeoAquaWatch, which Steve mentioned, he was the director and he recently stepped down, which is a community for water quality, dealing with remote sensing based water quality monitoring. And we are core group here. I mean, if you look at the water quality who is looking through remote sensing, there's a very limited number of people all around the world, the scientists. And it's always hard to sell to a stakeholder if you're measuring water quality through remote sensing. It's a tough thing. But Steve done some tremendous work through GeoAquaWatch. So great to that. And so my brief presentation will be on the remote sensing estimations of water quality dynamics in the Asian megadeltas. So I will take you from Costa Rica to Asia, basically Ganges and Mekong Delta regions. May I have the next slide, please?
Pointers.
Thank you. Great. So to briefly introduce what is Asian megadeltas and how the deltas are more important regions. If you look at any ecosystem, the fragility of the ecosystem or the volatile and how much anthropogenic pressures are going into the system. So that's defined by our human impacts and more recently in the last century, the climate change impacts. And if you look at the Holocene to Anthropocene and to the recent, we are more core into the Anthropocene, where we have the fresh, all the new ecosystems and everything is fine in the Holocene era and Anthropocene when we human era started. You can see that slowly lots of resources are collapsing and the deltas are most vulnerable ecosystems where when a delta ecosystem collapsed, it's easy. The lots of millions of people who are dependent on this delta region will be directly impacted with the socioeconomic and livelihood sources. And so to analyze the Asian megadeltas, we developed a bigger framework of social hydrology and in that fit into that water quality part where salinity is a major thing where the people directly depends on the water resources, but salinity is a critical factor that influencing people to adopt the agriculture practices. So that's why water quality is a critical factor in this entire framework of social hydrology and how we deal with from water resources variability, quantity, quality to how the societal response happens and how this information goes into the sharing, how the stakeholder response happens, and also at the same time, the agriculture, new adoption of the agriculture measures. And to briefly introduce you, we are initially planning to work on three Asian megadeltas, which is Ganges, which is Bangladesh and India, and Irrawaddy, which is Myanmar, and the Mekong Delta, which is Vietnam and Cambodia. But due to several reasons, we are not working in Irrawaddy majorly. So IMI is majorly working on Ganges and Mekong Delta regions. And if you look at the Asian megadeltas, they are more vulnerable to climate shocks and also anthropogenic impacts. They are highly intensively agriculture areas, and they are majorly rice-grown areas. And if you see it, so all of the area is like heavily rice-grown, and also from the last century, especially this has been intensified into double crop and triple crop also. And if you look at the salinity trends of the Ganges, in the top part where the Ganges Delta, where you can see the slow pockets, which showcasing the salinity is low. And if you, from the coast to the top, the salinity is year by year encroaching into the delta region. And this is from the 100 years now, from the 50 years now, how it will be. It's a tough to measure, but there is climate projections and everything, continuous monitoring going on, how to mitigate this and take measures to control it. One is tidal effects and sea level rise and the climate change, and also huge anthropogenic pressures. And the Mekong Delta is also same. If you look at the salinity trends, it's also the similar from coast to the upstream. The salinity is encroaching year by year into the delta region, where the lots of farmers depends on the rice irrigation for agriculture purposes, and they use this water for irrigation. But salinity is a factor that's limiting them. Sorry. So sorry. So salinity is a factor limiting them to adopt the new strategies and new rice varieties. And in these two deltas, salinity has become a major factor to influencing the irrigation patterns and how farmers are adapting as a double crop or single crop. The Ganges Delta, which region, one of the polders we are working on, the farmers are heavily using the groundwater in the upstream of the polder, where in the downstream they cannot use. So this majorly because the accessibility of the groundwater to the local people. And if you look at the alluvial terrain of the deltas, there is three layers. One is the upper aquifer, which is highly saline, and the second aquifer, which is second aquifer, which is a little bit around 100 meters. And the third aquifer is deeper aquifer, which where the, I already have one. So the third aquifer is the where deeper aquifer, where the most people depend on for drinking purposes. And the salinity dynamics are heavily linked to the socioeconomics of the delta system. And if we want to do the remote sensing based stability estimations and using Sentinel-2 data and link this with the salinity and turbidity of both these delta regions, and in broad, develop integrated models to link water and salinity to design the agriculture system design in Asian megadeltas. If you sorry if I speak loudly. So NDTI is a normalized differentiative turbidity index, where you can see the turbidity trends from the coast to the upper region. This is the Ganges Delta. And if you can see from the coast to the top, where the April is the dry season before the pre-monsoon, and in the upstream, especially where the high level turbidity, you can see it around 0.3 of NDTI. And whereas in August, which is a monsoon season, you can see the turbidity is drastically gone down. And this has a little bit variation when you compare to 2023, where the high turbidity values are observed in March, and whereas the September is the one where the low turbidity and after the monsoon season. So these trends are changing from year to year, depending on the rainfall patterns and everything. And so this map is briefly developed for the entire water bodies, but we have to mask it out to the only river bodies, then we can have a clear picture more. But if you look at the overall trend of the turbidity trends, especially the NDTI, and the monsoon has a very high impact. If you clearly see the trend from 2019 to 2023, so the turbidity drastically goes down when the monsoon season happens. And this is the season where the farmers are using the either rainfall patterns or flooded rice through canal irrigation and everything. But when they go to the dry season, where the canal irrigation cannot be used also because of the high salinity trends in the surface water bodies. And if you look at this, this is a direct salinity data, and previously NDTI, there is a direct link and correlation. You can see the pattern of the graph is very similar at the same locations. And the flood salinity is where the tidal incursion happens. Ebb salinity is when the tidal is releasing it. And both times actually, the salinity is a dynamic factor impacting the monsoon crop, and there is a dry season crop. So to further go into that, we want to develop a salinity forecasting model where we want to link the turbidity and salinity together, how turbidity has a direct relationship with the salinity and how this can be plugged in together. So that's where we want to develop this salinity forecasting model for specific to a polder, and later include the remote sensing based estimations also into the system. Then we combine with the in-situ monitoring, and we can develop a robust forecasting system. So this forecasting system will helpful for the farmers to estimate when is the good time to start a crop. And further bringing into the surface water, where we're talking about the salinity monitoring and everything. So the groundwater is a tricky part where the people heavily depend on the groundwater as well, but always the accessibility and also the which aquifer they want to tap into is also a critical issue. So that's why we want to combine the surface water and groundwater interaction modeling, where we initially we're developing for the polder system. So scale it up to in the next 3 years, if possible, to the entire delta system. So when we scale it up, so these remote sensing based measurements can be plugged into the model where we can do the seasonal patterns and estimate how entire delta system is drastically impacting, how we can develop different scenarios for the farmers, when to start the crop and when with the high water consumption and irrigation practices of the polder system and the Ganges Delta irrigation schemes in the Mekong Delta. So to conclude, actually, water pollution is a significant problem that influencing the cropping patterns and socioeconomic conditions, both in the Asian mega deltas. And high salinity in pre-monsoon or dry season affects cultivation in these deltas. Remote sensing based estimation providing critical insights into the seasonal patterns. But this is also a tricky part, actually, when we look into the remote sensing based estimations. They hold true for the most of the rivers, but some of the rivers, they don't give you any reciprocal, some good patterns. So that's where we have to do the in-situ monitoring and validate it more robustly and everything. So drawing the relationship between the turbidity, salinity, and density variations is very important. So that's where we are now, where we are linking the turbidity and salinity. And the other one is the density variations. So if you look at the GRACE data, GRACE is a satellite which you can monitor total water storage. So the GRACE gives you the density variations based on the gravity. And so in the deltas, especially, the salinity variations will be very drastic and dynamic. So we want to see how the GRACE can help us to any differentiation with the salinity with respect to the seasons. But the problem with the GRACE data is for the entire Ganges Delta, we have only 350 pixels. And for entire Mekong Delta, we have only 135 pixels. So that's a critical thing. We need to see how, because there's a 300 square kilometer area that each pixel carries on. So how the density variations can map into these regions, how if you want to look at the entire delta system, how that can be bring in. And we are currently doing the in-situ monitoring of different parameters with water quality. Then we want to validate all our data sets, remote sensing based estimations with the turbidity and salinity. So overall, our aim is to do the water quality management system that can inform agriculture planning within these two delta regions, and how comprehensive understanding of interconnectedness factors can shape the functions in these Asian mega deltas. And because these are very fragile ecosystems, so that's why we want to bring in lots of stakeholders also. So we're working with several stakeholders within these two deltas, and they can inform immediately what the model outputs are, and they are also involved in co-developing these models. So thank you. Sorry for my
even when your voice is out, I think all of us have benefited from this presentation. And if there are any questions online or here in the room, please raise your hands. Or yes, please introduce yourself briefly and then ask your question.
Thank you. My name is Laura Venegas, and I work for CATIA. This is a Center for Tropical Research and Research and Education. Sorry, to translate it in English. Well, my question is just to know about the scenario building that you put in your one of the last schematics. Do you consider to include climate change anomalies or other factors in order to build? I know that there is a lot of uncertainty, but there are products based on remote sensing and elaborated that could give some insights about the building of those scenarios, or if you already considered, maybe you can clarify. Thank you.
So in general, to briefly introduce, IMI is a research for development organization. So we want to, generally for any hydrologist, they go and develop scenarios, what they think of. And normally I also used to do the same. But we reached out to the stakeholders. They're all involved in a workshop, and we're asking them, if we develop these models, what are the scenarios we want to include? So they gave us critical inputs. This happened in early this year. So which scenarios to develop? So we came up with the 4 scenarios, which is on the climate change impacts, of course, and how the anthropogenic impacts relate to the irrigation patterns, and also specific inputs, how the salinity dynamics with respect to either domestic water consumption or the irrigation water consumption, and also specific to the crops. The other one where rice is the major crop, but there's other cash crops also going on recently with the shifting from rice to the cash crops. So based on these major 4 scenarios, we want to inform stakeholders different management strategies, what we can do with the hydrological modeling, combining remote sensing and in situ data.
Are
I
there
have
any
a
other
question
yes?
from the online audience. It says, greetings from Kenya. My name is Nancy. Thank you for your presentation. My question is, how often do you update the salinity data?
So currently for the remote sensing based estimation, we can get it for every monthly twice, mostly, but we are aggregating the monthly data now. But the in situ monitoring, we are doing it 3 months once in Ganges Delta and monthly in Mekong Delta. So this because of the logistic issues, nothing to do with the specific monitoring system.
We have another question from Shanlong Lu in the room.
Sorry, I forgot to introduce myself. I'm Shanlong Lu from the Aerospace Information Research Institute of Chinese Academy of Sciences. My question is that I just saw that you're using the historical measured salinity data to get the background of the salinity of this kind of delta. And then you're using the measured or forecasting discharge to reverse or to forecast the future salinity. If the background of the salinity is changed, how to solve these problems?
So salinity is majorly impacted by the tidal incursions. So what we want to see if from the upstream, so the Ganges water coming from the very upstream where the India releases the water coming into the Ganges Delta. So when the discharge with respect to the seasonal trends of the discharge, how with respect to this discharge and the salinity is going on. And also there is a flood and ebb salinity where the daily, subdaily pattern. So that's secondary. And the third one is the tidal incursion, where this subdaily of flood and ebb thing going on. So seasonal tidal incursion, how is this going on? So these 3 are very important to go into the salinity monitoring, but discharge is the critical one. So that's why we primarily concentrate on the discharge. How much is the discharge coming in from the upstream? Because if you look at the monsoon season, the discharge is very high. And based on that, the salinity is also low in the monsoon season. And if you look at the dry season, the discharge is very low. And at the same time, the salinity is very high. So we want to see how the discharge can influence the total forecasting system.
Is there one more question? If not, then we'll have a chance to ask more questions in the discussion later on. But I would like to move to our next speaker, who's using more quite modern techniques for his research. And the presentation is on hyperspectral imaging and artificial intelligence for the detection and quantification of agrochemicals, such as chlorothalonil utilization in Carta O. Alexander Solis Quesada is going to be present, and he works at the Delta Lab at the Instituto Tecnológico de Costa Rica. Alexander is a technician and industrial maintenance, in industrial maintenance, and an active student of mechatronics and engineering. He's also an active member of the investigation lab named Delta Lab. Alexander, the floor is yours.
Thank you very much. I'm very glad to be here and very honored. I think that I'm the first Costa Rican presenting today. So first of all, I would like to welcome you all. I hope that you're enjoying this beautiful country, its beautiful people, and that you have a great stay. So yes, this presentation will be a little different from others because I'm bringing you a proposal on a project that is still on diapers. So we're going through some of the concepts that we have planned for this mission. Okay, so here's the content that we'll be covering today. First, we're going to start introducing you to a problematic that is very concerning in the presence of Costa Rican. And also, I'm going through some background research. Then we're going to talk about the mission objective, its timeline, and concept of operation. And we're going to finish talking a little bit about those key performance parameters or objectives that we want to achieve through this project. So Costa Rica is quite famous, and we are quite a little country. So it's mainly that fame. It's mainly because we are promoted as a green country, and I don't have any doubt that you have already seen it with your own eyes. Costa Rica is such a beautiful country. It's full of nature, and well, I'm very proud from being a Costa Rican and of all the work that we have made for this to be this way. And it comes to my mind talking about how we almost only depends on clean energy sources, also about the whole environment conservation, but there's not only good news. And here in Costa Rica, we have a very concerning problem, and it's the use of agrochemicals, the abuse of agrochemicals. So it may be surprising for you to know that here in Costa Rica, we have drinkable water from the tap. That's something that's not common in all the countries. And this privilege, because I think that that's a privilege, it's on risk because water sources are being contaminated with agrochemicals. And the last UNDP reveals that Costa Rica is the #1 country in the world also in the use of agrochemicals. And the main concern comes when we start seeing what these agrochemicals can mean to health. And most of these substances are very dangerous for human consumption and also for other native species here in Costa Rica. And more recently, in a couple of years ago, chlorothalonil was banned legally here in Costa Rica. And it was because it was detected that it contaminated Asada, that is like the facility that distributes water here in Costa Rica. And this happens in Cartago. That's the province in which I live in. And okay, just to point something very important, the agrochemicals that are used on crops, they wash. And we today have heard about how water drains and goes through underground sources. And here in Costa Rica, the main source of drinkable water is underground water. So I'm going to talk a little bit about the background research that fundaments this project. First of all, we question ourselves, how are we detecting the presence of dangerous substances such as chlorothalonil? And the answer is that in Costa Rica, the main lab is located in the Universidad de Costa Rica. And they take samples from superficial and also from subterranean water sources, and they test them through hyperspectral samples. So this kind of test can also be made in soils, fruits, and vegetables, but this is out of the scope of the project. The important part here is that this testing requires a lot of time to really testify that water source has been contaminated. We need proofs of presence of agrochemicals throughout several years. And also, this test requires specialized personnel and specialized equipment that may rise its costs. So what are the alternatives? We are, yes, so we are considering hyperspectral imaging data because there has been some recent studies in Japan in crops and in products that has been successful, and that they say that it really is possible to identify the absorption spectrum of an specific agrochemical in a plant through this kind of images. And also, so if you're not like very specialized in hyperspectral imaging, they are like a photograph. So the difference is that a photograph is an array of numbers that normally contains the amount of red, blue, and green that there is in a single pixel. So in this case, these special cameras, hyperspectral cameras, they are the same. They are an array of pixels, but in each pixel, we have information about how much light there is being reflecting or absorbing in different wavelengths. Okay, so these images are highly dense when we're talking in terms of data. And there's where the artificial intelligence comes in. So when I tell you about artificial intelligence, I'm talking about a convolutional neural network, which is a network that has its own characteristics. We think that this is the best approach to the problem because these kind of networks, they can work with big inputs like an image. And they can be trained to identify patterns. And for example, there's a really known exercise when we are learning about artificial intelligence networks. There is a convolutional neural network that identifies from a picture what number is there written. So any of us writes different. We have our own handwriting, and the ability that the AI have to identify the patterns and the characteristics and to really generalize that problem and understanding that if I write a 2 different that you do, it's the same number. That's what we call deep learning. So we're trying to put these two technologies together. And this leads me to the objective. So what we want is to generate a tool that identifies the use of dangerous agrochemicals, such as chlorothalonil, through hyperspectral Earth imaging data. And we have to start with a viability study, and we're going to do it through drones. So we're going to equip drones with hyperspectral cameras, and we're start collecting a large amount of data, because there's a relation between the amount of data AI needs for its training and the difficulty of the problem. So in this case, we have a lot of variability because we have different species, we have different kind of agrochemicals, and different linings in each photograph. So we need a really big amount of data. And then we're to our neural network for it to get trained. And afterwards, we're going to test the results by showing the artificial intelligence some pictures that it hasn't already seen in its training. And this will really give us a good image, or how do you say it? Like a perception of what may be the precision that we are looking, or that we are going to try to get with this tool. So the next step will be scaling this work for it to work with satellite hyperspectral imaging. And this is very important because even though I'm from Cartago, and we want to attack the problematic that there is in this province, and I'm sure that this problem it's present in all of our countries, and we have to really start taking care of the water. So through this application to satellites, we can start also monitoring the presence of dangerous substances in other countries and other regions. And well, here it comes like a difficult part, because when we escape from drones to satellites, there are a lot of variables that comes in and that we have to take in. Some were already mentioned, but for example, clouds and other meteorologist phenomena, it's very distorting to our measurements. And also the resolution may vary, and the amount of landscape that we are observing in each photograph may vary. So here is an important part of the work. It's to identify all the variables and take them on count. And evaluate the results that we're having with software here on Earth, with an AI trained on Earth. What we want is to deploy a real-time detection system on a satellite. So here is the concept of operation. What we want is to have a satellite in orbit that it counts with a hyperspectral camera, but it also has uploaded the software that we're going to develop. So in real time, it's going to take photographs, and it's going to send reports constantly to Earth, telling us how much and what are the substances that it's detecting in the different landfills of crops. And here in the Earth, we can download that information, analyze it, and really to the decision makers and other stakeholders. Which are the goals that we're going to achieve? And this is like order in yes, like chronologically, what thing that it will be. And all of these steps will be recorded and document, and probably we're going to make a publication or two about each of these. So first of all, we need to start identifying the absorption spectrum of agrochemicals, starting with chlorothalonil, because even though it has been legally banned in Costa Rica, we suspect that it's still on use, or there are substances really similar to it still on use. So the idea is to identify this through hyperspectral imaging data. Then we need to see if it's viable to collect data through drones equipped with these special cameras. And the next step will be identifying the hyperparameters of the convolutional neural network. And this is very important. we need to optimize these hyperparameters because the computational resources that we have on satellite are really limited. So we need a really optimal software. Next up, we're going to train the convolutional neural network, and we're going to start testing how good it is at identifying the presence of agrochemicals and also the amount of them that there is. Afterwards, we're going to scale it to experiment with satellites. This is the most emotional part. And lastly, we're going to deploy a real-time satellite application for the detection of agrochemicals misuse, hopefully in making an application that is open for all the world to use. I'm already finishing, but I would like to mention that the idea is not to convert us in some kind of agrochemical police, but what we want is to raise concern and start like sending help, because in most of the cases the use of these substances is not because people want to do harm, but because they don't know the harm that they are doing. And thank you so much. And if you have any question or feedback, I will be very happy to hear it. Okay.
Thank you very much. I see we have a question. Please introduce yourself and ask your question.
I'm Sumaya Muhammad from Egyptian Space Agency. I'm actually a communication designer or system designer. My question is about how you classify the type of chemicals according to the wavelengths of each hyperspectral.
Okay, so mainly it's through its absorption spectrum. It's like a fingerprint for each substance, and it may vary between each species of crop. So that's why it's part of the experiment or the project to start identifying which is spectral, the absorption spectrum of that agrochemical in each crop in a special, well, like especially. And also, well, no, that would be.
So this means that each chemical type have a different footprint than the others?
Yes, correct. And the absorption spectrum of a substance will depend only on, well, the surface in which it is put, but also the chemical composition, and that you can cover that with anything.
Okay, thank you.
Oh, thank you very much, Alexander, for an interesting presentation. You said that it's possible to do some scaling also. And for within a country, I think there would be less amount of conflicts or resistance. But if it was at a transboundary level between countries, then where do you see this particular technology being applied with particularly relating to the differences in terms of methodology, in terms of thresholds or ways that you apply that method, for looking at different chemicals and categorize would differ for each country, and whether you would have some kind of a agreement or disagreement on that.
Yes, a very important part of this project will be how big and strong of a network we can do with entities that represent all the interests of the society. So we need to have people that represent farmers' interests, and also in public relations. And transparency is a very important part of this project, and it's something that it isn't always like that in water quality topics. Are going to document every single step for it, that if any country want to approach us and will help us and also replicate what we are doing, they can do it because what we want is not just the application, but the results and the impact that it will have on farming culture.
There's another question. Please go ahead.
Thank you. The idea, I think it's interesting, but I was just wondering, how can you capture a very tiny particle that is at the same time moving and at the same time could be like together with other particles? If in the lab is difficult, I wonder to do that by a drone or whatever, that it may have some kind of resolution. I mean, the idea seems interesting, but I don't know how feasible that is.
Yes, that's why the viability study is very important, and it may reveal that the precision that we have isn't that big, because you're in the truth here. It's going to be very difficult, but maybe it can give us hints to where to look with laboratory tests. So, for example, it will help us to go and test some areas that may be contaminated, and we can't really tell the amount of contamination, but we know that there's something that we have to look at that place, and that's the idea.
Just to follow up, it's okay, Nina. To his remarks, because I'm a little bit confused myself. So we're going to start with a given matrix like water. I mean, like DI water, and add given concentrations to do some kind of systematic build up some kind of calibration, or at least see if it works, or is this to put on plant leaves, soil? And again, the concentrations I would think in sub microgram per liter. Are you going to be able to detect that with your sensors? I'm just wondering how far down the road you've gone and have where it's shown promise.
Well, as I was telling you at the beginning, the project is still in diapers, and there's a lot that we don't really know accurately. But yes, the idea that we have for the beginning of the project is to start on plant leaves of certain species. So, for example, in Cartago, the crops that we mainly have are potatoes, onions, and stuff like that. So we're going to start with some test fields in which we can, well, see the amount of, or how the spectrum of absorption is, how it varies when we apply these kind of chemicals. And also we need to take on count, for example, the irrigation of the land of the farm, also rain, for example. There are a lot of variables that we have to take in count, and that we are going to try to really consider. But yes, it is still like a very beautiful thing when you just think about it. But when you start digging up, there problems start to appear. But we in academy love problems, no?
Thank you so much. I also have a follow-up question, but then I would like to open the floor for questions on all presentations again, because we have time for a discussion in this session. But my follow-up question is, generally speaking, when we do water quality assessment with hyperspectral imaging, how well do we detect the presence of specific agrochemicals in the water bodies, not on the plants necessarily? Can we do that, and how far can we do that? And maybe Mahesh Champani can also speak a little bit about how his experience with the rice crops was in the Asian mega deltas. Do you have any experiments on that?
Sorry, I didn't get that question, Gail.
So have you had any experiences using hyperspectral imaging in the Asian mega deltas? Because you mentioned rice crops are present in the area. Have you focused mainly on salinity sensors?
So I'm focusing on salinity. My colleague, who is not here today, so he's doing rice mapping of the deltas. So they're using that, yeah.
They're using it?
Yeah.
And do they have experiences with the different substances, like the different agrochemicals
No.
affecting the water? Okay.
I'm wondering how this is possible because agrochemicals is a typical chemical, but even tough to measure in a lab actually, because you have to go through lots of species differentiation, the chemical species differentiation. So wondering, I mean, if it's results are come up, just please let us know.
Thank you. Thank you.
So in the research that we made before presenting this project in the university, we saw that it's already being done in a small amounts. So for example, there are some certifications for farms that requires that they pass as clean of agrochemicals, and on small samples in a laboratory, it's possible to identify the agrochemical through hyperspectral imaging. So the scaling it to more further photograph is the part that I'm not sure if it could be made.
Thank you very much for your presentation and good luck with the research. I would like to open the discussion now to all the presenters.
To say something about the hyperspectral camera image.
Okay.
Our colleague in Egypt, they work in using the image of hyperspectral camera for climate change to decide or to draw the map for concentration of CO2. So by the way, they can do for chemical because they see what's the observation of the wavelengths for each type of chemicals, and they can draw the map for that concentration. That's all.
Thank you very much. Are there any questions for Stephen Greb on his presentation, or for Mahesh Champani on his presentation on the Asian mega deltas? Do we have any questions from the online participants? Okay. I will have a few. So in terms of in situ data availability, Stephen, you mentioned a few portals that can be accessed to retrieve samples at certain conditions. Where do we stand with the different parameters that we want to observe in terms of the availability of in situ data, and for which regions are they generally available and not available? Where are the gaps when it comes to in situ data, and what can be done to improve the situation?
Yeah, well, we touch on that just a little bit at the end of my talk. I think there is a lot of gaps. Where to begin? I don't know. I would say we probably have the most coverage in places like the U.S. and in Europe. I think, when we're talking about doing CalVal work with satellite remote sensing, we like to have some optical information collected, not just the end water quality parameters, such as chlorophyll or suspended solids, but information about the absorption properties of the water or the backscattering of the water, and those are even rare. There's small groups or research or investigators around the world that are using that use that kind of equipment. At the validation meeting last year, we talked about, could we raise funds for a community set of equipment, like a traveling set somewhere where this these instruments could be shipped around, or people could be trained on them, because you're not just going to ship them off to somebody who's never seen it before, but because they do take some mentoring or getting used to them. But so, there's options like that have been discussed. We are going to come out with a publication, or would be submitted soon, which will have a list of recommendations from this workshop. So I'm hoping in there there'll be more and broader idea of what and where we need to go. There's we have some sense of who is doing what now, and some sense of the gaps, but not all. And we're hoping, again, as more sensors and sophistication is improved and some of these algorithms, that we won't need the validation work as much as we do now. But I mean, that's a ways off, and I wouldn't want to comment more on that.
I do understand that there's also a difference in the time that a water sample needs to be brought to the lab for different parameters. So in some areas of the world, we see issues with labs being in the vicinity of the areas where the samples are being taken. Is that correct? And how do you think this problem could be addressed in order to get more samples done? I think the Atomic Energy Agency, they have a laboratory network that they launched at the UN Water Conference in 2023, hosted in New York, and I think maybe there is potential. They're using it for other purposes, but I think it'd be great if the space community could get in touch and cooperate there.
That's a good, I mean, I didn't know that, but we'd definitely be willing to talk more about that, or what its capabilities are, or what the needs of our community would be. But yeah, there's definitely timing issues and getting samples to the lab, and just getting access to the water bodies. Being able to get out on the water is problematic in some areas. I mean, boats, logistics, it's hard.
I see a question from Mandira.
Well, thank you, Stephen, for your presentation. I think one of the issues that you highlighted was the use of citizen science to collect data and for validation and calibration. So that it probably adds to the in situ data, a little different, I guess. So what are some of the challenges that has been faced in terms of the using this particular method of collecting data, because this involves quite a lot of capacity building of the locals as well as awareness, and how far there has been a challenge in terms of the accuracy of the samples that are being collected versus what actually is being measured.
Right. First of all, I would just say we love our citizen science monitoring people. They're very good. And I think I mentioned that they're really vigilant about getting out there on the days we ask them to. We give them a little calendar which shows which days the flyover is of Landsat 8, Sentinel-2, and then they mark it on their calendar in the kitchen, and then they go out on the lake and collect the sample when the satellite's coming over, provided it's not thunderstorms or something like that. There is a learning period. We do screen these people. There's trainings that they're required to take, and they do have to go out and do a Secchi disc, if you will, and we check it based on what we have. But we have found most of them to be very vigilant and conscientious about what they're doing. A lot of them are retired engineers or scientists or teachers, and they've done very well. We actually had kind of a Secchi disc contest between some of the local water resources staff and the citizen science people, and their variability and and their accuracy was actually better than the water resources staff for where we'd sampled. So yeah, I have a fair trust in citizen science, but we don't ask them too much. We don't, and they're not doing a lot of things which would require a lot of training and background. It's basic things like water temperature, Secchi disk, clarity, things like that.
If somebody wanted to replicate the citizen science experiment, let's say in their region, how much effort goes into scheduling, like making the appointments of the satellite overflight, like these plans for what kind of area, and how long do you need to train them before they can go into the field?
Yeah, well, one, I'm not, that's not my role in this, so it's not a thing that I have that much experience with, but I mean, I think it doesn't take long to do the training, but again, they have to read the materials. I think they might even take a little test. If they're interviewed. I can't remember what your other part of that question was.
How much time do you use for training them? Like how long do they have to undergo training before they're ready to go to the field?
Right. I would say we would run these trainings a couple times a year, and it's just open to the public for them to come. We work not just with the citizens, but what we call our extension agency, or agency which does a lot of work with the public, and they have someone who's dedicated to doing this training. We don't do the training, but we actually have materials, printed materials for handouts that we use. So those materials are available.
Okay, thank you so much. Are there any other questions? Are there questions on the presentation of the Asian mega deltas, maybe online or in the room? We heard a lot about salinity intrusion into the river, depending on the monsoon season. Crop planning for farmers, informed decision making. If not, let me ask you, Mahesh, what are the next steps in your research in that area? What are the pressing challenges that need to be addressed?
So in general, we want to develop this salinity model, so where we can inform local communities and the farmers when is the high salinity going to be increased. Salinity values are low, so they can start the cropping season with respect to rice or any other crops. So that's the next steps. So where we want to full-scale model development and giving it to the local stakeholders, and also, yeah, that's my slide.
Okay, thank you.
And related to the in situ data, actually, there is lots of
Can you increase the volume a little bit?
So there might be a lot of stations already there in North America and Europe, but there is a lot of in situ data not available in majority of Asia and majorly in Africa. But AMCO, which is the African Council of Ministers for Water, so they are taking initiatives to how to develop this in situ, develop the local stakeholders, doing the capacity building to them, and then taking more samples. Yeah.
Thank you. Okay, then I would say we can wrap up the session. We've heard a lot about monitoring various water quality parameters in water bodies by use of Earth observation data such as chlorophyll, turbidity, salinity. We've also heard about the use of GRACE data to assess relations between turbidity, salinity, and density variations, and the involvement of stakeholders to define better decision-making tools for crop decisions. And then we've heard about a project idea, I would say, or project plan on how to monitor agrochemicals that are affecting our health by using hyperspectral images. And if we get any results of your research at some point, Alexander, I think, please share them with us. With that said, I would like to thank the speakers, and we'll continue with the theme of water quality, both in our next session, but I would also like to announce now